people, it's me, Devikesh Pandey, and I am back with chemistry. I'm back with solutions, and I am back with a fun fact about solutions. So, I am pretty sure you might know this, but if you don't, so light can never pass through a true solution. A ray of light, you try to pass it through true solution, not possible. True solution, what is that? You all know it, you've learnt it. A true solution is a solution where the solute dissolved in the solution has a particle size of up to only or even less than 10 to the power minus 9 meters or 1 nanometer. Okay, that is a true solution. So, I just discovered that fog is not a true solution. You might say that I have said before that air is a homogeneous mixture and it is a solution. But it is not a solution. It is not a true solution. It is a colloid. You could say it's a colloid because light can pass through it. You can see infrared rays through a fog, or you can see light through a fog, right? When you're traveling, even in the most densest fogs of Delhi. Most dense. Densest is not a word, I'm sorry. Okay, so last time we talked about how we are going to express, concentrations in solutions. Today we are going to be continuing with what is actually the most important thing in this chapter, and that is solubility. How would you define solubility? The amount of substance you can dissolve in a solvent. That is the solubility of the solvent. That is what solubility is. Right. So, if there is solubility, then it can vary with what kind of substance we are trying to dissolve. So, what factors does solubility depend on? 1. It depends on the nature of solute. 2. It depends on the temperature. 3. It depends on the pressure. Okay. So, not just the solute, it also depends on the solvent, because you might have heard the theory of like dissolves like. For example, polar solvents dissolve polar solutes and non-polar solvents dissolve non-polar solutes. You try to dissolve, a very bulky, long chain, long branched organic compound in water, you won't be able to do it because water is a polar solvent. Okay, so let's begin. Okay. Let's talk about the solubility of a solid in liquid. Okay. Have you ever tried to dissolve sugar in water to make chashni? If you haven't, go try it. You will understand what I'm going to say right now. When you try to dissolve sugar in water, you reach this certain limit where you can't dissolve any more sugar in it, right? It just doesn't happen. No matter how much you stir it and how much force you apply on it, it just does not happen. Then you go to your mother and you ask for her help that, Mom, that sugar is just not getting dissolved however much I try. And your mom is like, just heat it up. Increase the temperature and your sugar will get dissolved. You have your answer. You go, you heat it, and your sugar gets dissolved. You add more sugar, you keep heating it, your sugar gets dissolved. So you can say that, it is the solubility of a solid in liquid increases with temperature when temperature is increased. Why do you think this happens? This happens because dissolution of sugar in water is an endothermic process. Okay, it requires energy for the dissolution to happen to break the bonds between the sugar molecules so it can get dissolved in water. It is an endothermic process. So if it is an endothermic process and you're supplying more heat to it, then that means that you're giving more energy to the left hand side of the reaction, and according to equilibrium and according to Le Chatelier's principle, the equilibrium is going to shift to the right hand side and the sugar is going to get dissolved. So for a solid or any solid in general, solubility increases as temperature is increased because dissolution of a solid is endothermic. In liquid, it is endothermic. Okay. Now let us talk about dissolution of a gas in liquid, or the solubility of a gas in liquid. It is the complete opposite for that of a solid. As temperature is increased, the solubility of gas in liquid decreases. Why? Because solubility of a gas in liquid is a completely exothermic process. By exothermic, I mean it releases energy when the reaction begins. Endothermic means it absorbs energy. Exothermic means it releases energy. So if it is releasing energy, which means we have energy which is coming out at the right hand side. Now, if you're supplying heat to it, then you're giving it more energy on the right hand side. If you give it more energy on the right hand side, then according to Le-Chatelier's principle, the equilibrium is going to shift back to the left hand side. And if it shifts back to the left hand side, then it means that our gas is not going to get dissolved. So if you increase the temperature, solubility is going to decrease. Same as for pressure. For gases, you require high pressure for it to get dissolved in a liquid, while for solids you require low pressure. Okay. Do you get the comparison? Okay. So now let's just move on with this. And when we talk about solubility of a gas in liquid, there is this certain law made by a man named Henry. It's called the Henry's law, and it deals with the solubility and how it is related to its concentration in a liquid, the solubility of a gas, and how it depends on its concentration. So what Henry law states is that the mass of a gas dissolved in a given volume is directly proportional to the partial vapor pressure of the gas present above the surface of the liquid. Or you can say that the solubility of a gas in liquid is also, directly proportional to its partial vapor pressure present above the surface of the liquid. Okay? When you write this statement in the board, word to word from the NCERT, the board is not going to give you a complete mark unless you state an expression. And that certain expression is small p directly proportional to xi. What is xi? From our last video, we know that it's mole fraction, right? So, small p directly proportional to xi. Then if we have to remove the proportionality sign, we go P is equals to KH xi, where KH is our constant of proportionality. Okay. And it is called the Henry's constant. Well, it's that man's law, so the man is going to name the constant by himself too, right? So now this has a certain relation with our solubility as well. Before we go to that relation, this is a dimensionless unit or a dimensionless quantity. Also, its unit is the same as pressure, bar, ATM or K bar, whatever you like to say. And the relation between this and solubility is that greater the value of KH, lesser is the solubility of gas in a liquid. Lesser the value of KH, greater is the solubility of a gas in liquid. That pretty much about sums it up what Henry's law is. Okay, and there are a lot of questions that come to, you can say, there are a lot of questions that can be formed from this. One is one of the favorite questions of the board is, gas A is more soluble in a liquid than gas B is at the same temperature, then whose Henry's constant is greater? So now I told you, solubility inversely proportional to KH. If it is inversely proportional to KH, then since gas A is more soluble, then it has a less Henry constant value. Gas B is less soluble, so it has a more Henry constant value. Okay, now obviously if there is a law, then there are applications, and let's talk about some of those applications. Okay, the first application of Henry's law is aerated drinks, carbonated drinks. You have carbonated drinks as an example. You have, let's say, these days, earlier scuba divers used to use nitrogen and oxygen mixed cylinders when they used to go scuba diving. Now they use a mixture of helium and oxygen. Why? Because when they used to go underwater under high pressure, at that point it did not matter whether it was nitrogen or oxygen in their lungs, because at that point nitrogen was soluble in their bloodstream. But when they used to come up to the surface, then the pressure used to decrease and the solubility of nitrogen in the blood would also decrease. So it would come out in the form of gas. It would accumulate at certain parts in their body and cause an you can say unfathomable pain and very torturous pain called bends. It used to cause that in them, and that is why they stopped mixing nitrogen in it. Another illness related to the Henry's law, you could say, is anoxia. It happens when you go to higher altitudes, again where pressure is very, very low. So solubility of a gas and liquid decreases. So solubility of oxygen in our blood, it decreases. So we become weak-minded. We lose our, we do not lose, but our ability to think is obstructed, and we experience symptoms like fatigue and tiredness. So that happens too. Okay, so that pretty much sums up what our applications of Henry's law is. And Henry's law has certain limitations, because since we're talking about the solubility of gas, then there are limitations, because if temperature is high, then you can't say that Henry's law is applicable. So first, when temperature is low and pressure is high, that is the first limitation of Henry's law. And second, gases, they do not undergo compound formation when they are getting dissoluted. So that is another one of the limitations of Henry's law. Okay, so let's move on. Now, since we've discussed this, let's move on to say, okay, now we've discussed what Henry's law is. There was another guy who came up with a similar law, and his name was Raoult. Now, he basically, both these laws state the same thing, but since it's in our course, we have to study it. Now, Raoult's law, there are two different Raoult's laws for one, you can say a binary solution of two volatile liquids and a binary solution of a non-volatile substance and a volatile substance. So, for the one that has volatile substances, Raoult's law states that the partial vapor pressure of each component in a solution of two volatile liquids is directly proportional to its mole fraction in the solution. This is the expression again, P directly proportional to xi, or P is equals to P naught xi. What is P naught? P naught is the pure vapor, the vapor pressure of the pure substance at room temperature. That is P naught. Okay, so that is what our Raoult's law states. Okay. Keep in mind, these two laws are pretty similar, but they are also different. Okay, because the constant is different, right? So that is important to be thinking about. Okay, now there are certain expressions that come into play when we are talking about Raoult's law. The first expression that you have that you get to use in your numericals. Now, if say there are two components in our solution, A and B. Okay, so then the mole fraction would be xi A and xi B, right? And the partial vapor pressure would be PA naught of pure component and PB naught. And then the partial vapor pressure in the solution would be PA and PB, right? Now, PA would be equals to PA naught xi A and PB, small p, these are all small p's, okay? So PB is equals to PB naught xi B, right? Now, say you were to add these two equations, okay? Or let's say you were to just add it, okay? Don't subtract it, please. PA plus PB is equals to PA naught xi A plus PB naught xi B, right? Now, we learned when we were talking about mole fraction that if it is the mole fraction, we're talking about only two components liquid, or we are talking about a binary solution, then it is like probability where the mole fraction of the other component is 1 minus the mole fraction of the first component. Okay, so you can either write this as 1 minus xi b or you can write this as 1 minus xi a. Okay, so let's do that. PA plus PB is equals to PA naught xi a plus PB naught 1 minus xi a. Okay, now over here you multiply it, what you get is PA plus PB is equals to PA naught xi a plus PB naught xi a plus PB naught. Take xi a common, PA plus PB is equals to, this is basically you can say the partial pressure of the solution. Okay, we are taking xi a common, right? Xi a, PA naught plus PB naught plus PB naught. Okay, so well, that is pretty much what our Raoult's law equation is. Now any one of these equations you might have to, work upon during your numericals. Okay, any one of these. It can be any one of these. Okay, so that pretty much sums up our Raoult's law equation. Also, if you want to calculate the partial pressure of a certain component in the liquid, then if P total, PA, say you want to calculate and you know that the total partial pressure is P total, okay, and the mole fraction given to you of that particular component is YA, then partial pressure of A would be P total into Y of A, or P total, you could say P total would be PA upon YA. Okay, so that pretty much sums up what our Raoult's law is. Now, based on Raoult's law, there are two types of solutions. Actually, yeah, two types of solutions. The second part has subparts. The first part is ideal solutions, second part is non-ideal solutions. Let us learn that through the differences between them. Okay, if you are making notes, divide your page into two parts. Give one heading as IDEAL and the second as non-IDEAL. Okay. First thing about ideal solutions and non-ideal solutions is that ideal solutions, they act in according to Raoult's law. In accordance with Raoult's law. Okay. And non-ideal solutions, they do not act according to Raoult's law, or they do not show the results which are expected by Raoult's law. Act in accordance to Raoult's law. Okay, that is the first very major difference between them. The second thing about ideal solutions is that our the interactions between the solvent is equal to the interaction between the solute and the solvent after dissolution. So basically the energy on both sides is same. Okay, and while here in non-ideal solutions, our solute and solvent is not equals to our solute-solvent interactions. Okay, so the attraction or repulsion between them is not the same. Right. The third thing is our delta H of mixing. Delta H is energy of mixing is also zero, and our delta V mixing or volume of mixing after is also 0. It's 0. While here it is not equal to 0. Delta H mixing and delta V mixing not equal to 0. Okay, so Ideal solutions follow Raoult's law. Non-ideal do not follow Raoult's law. Okay, that pretty much sums up what this is about. Now, I told you the second one, which is non-ideal solutions, has two parts also. Let's discuss those two parts. Right. The first type is solutions showing positive deviation from Raoult's law. Positive deviation, I will tell you what it means, and divide your page into two parts again. And solutions showing negative deviation from Raoult's law. Okay. Now, what do I mean by showing positive deviations is that whatever result that you were expecting from Raoult's law, it is always less than what we have actually got, or what the result that we have got is always greater than the expectations from Raoult's law. So we talked about, does it follow Raoult's law or not? No, it doesn't, obviously. Now, in positive deviation, our solute-solute, solvent-solvent interactions are always greater than our solute-solvent interactions. Okay, now what do I mean by the solute-solute and solvent-solvent interactions being greater is that due to this, the partial pressure of individual components is greater than partial pressure of the solution. So that is what it means, that the result is greater. The partial pressure expected from Raoult's law is always less than what the solution actually shows. Okay, then like I said, partial pressure of each component is greater than P total. Okay, and also our delta H mixing and delta V mixing is also greater than 0. For negative deviation, this gets flipped. Basically, for negative deviation, this changes to a less than sign, this changes to a less than sign, this changes to a less than sign. Okay, so now what this means is that the partial pressure shown by the solution or presented by the solution is less than what we expected from Raoult's law. So the Raoult's law expectation is greater than what we have actually got. Okay, so that pretty much sums up what positive deviation, negative deviation solutions are. Now, positive deviation and negative deviation solutions, they give rise to something called azeotropes. Now, what does azeotropes mean? Azeotropes are basically solutions that solutions, binary solutions with components that boil in the same phase. Okay, or that have the boiling point in the same phase. Okay, so those are azeotropes. Right. Now, azeotropes is a very ulta thing when it comes to positive and negative deviation, because positive deviations show minimum boiling azeotropes, while negative deviations show maximum boiling azeotropes. Okay. Okay, so that is what azeotropes are. That's all for today. Tomorrow we will be discussing the another most important part of this chapter, which is called colligative properties. And colligative properties are pretty much very. That's all for today. Now we are going to be talking about in the next video we will be talking about colligative properties and what they are and what importance they show in this chapter. And you, from your past experience, you may know that they are important because most of the numericals from this chapter in the board come from colligative properties. See you. Bye bye.